Most people imagine global communications as something abstract, wireless, or floating in the cloud. But in reality, nearly all of it moves through physical infrastructure resting on the ocean floor. Thousands of kilometers of armored fiber carrying financial transactions, military communications, cloud traffic, and diplomatic data as pulses of light through glass. These cables are not symbolic, and they are not theoretical. They are engineered systems laid deliberately across mapped seabeds, amplified at regular intervals, repaired, monitored, and, critically, accessible under the right conditions. This is the physical layer beneath everything we call digital, a layer governed not by protocols or policies, but by optics, materials, science, and geometry. Once data enters this environment, it obeys physics first and security assumptions second. And before we talk about encryption, quantum protocols, or proofs of security, we need to understand where information actually lives, how it moves, and why the ocean floor quietly became one of the most strategically important attack surfaces on Earth. What you're looking at here is not a map of the Internet in the abstract sense. It's a map of where global communications become physically compressible. Because despite how we talk about cloud services, satellites, and wireless networks, over 95% of intercontinental data traffic moves through glass fibers resting on the ocean floor. And that traffic does not distribute evenly across the planet, but instead funnels through a small number of geographic choke points where multiple high-capacity subsea cables converge, terminate, amplify, and redistribute signals, creating locations where interception is not only possible, but operationally efficient. The first of these convergence points is the U.S. East Coast transatlantic corridor where financial markets, cloud backbones, and government communications between North America and Europe are terminated in a dense cluster of landing stations that sit within tens of kilometers of each other, meaning that redundancy in routing does not imply redundancy in exposure. Because gaining access at this point allows an interceptor to sample an enormous fraction of outbound and inbound continental traffic without ever touching a single logical endpoint. The second convergence point is Western Europe, particularly the United Kingdom, Northern France, and the Netherlands, which together function as Europe's optical intake valve for traffic arriving from North America, Africa, and the Middle East, aggregating signals into trusted infrastructure that depends on regulatory, legal, and physical assumptions which quietly fail under coercion, compromise, or intelligence access, turning what looks like a distributed network into a small number of physically exploitable facilities. The third convergence point lies in the Mediterranean into the Red Sea, especially around Egypt, where geography forces cables carrying Europe-Asia-Africa traffic through a narrow corridor with no meaningful physical bypass, making this region one of the most strategically leveraged interception zones on the planet, because control here does not require breaking encryption universally, only observing enough traffic for long enough to extract value from metadata, redundancy, and leakage. The fourth convergence point is the Persian Gulf and Arabian Peninsula, where Europe-Asia-India traffic is funneled through a limited set of coastal landing sites embedded in environments characterized by extreme infrastructure concentration, state involvement, and trusted node assumptions that collapse as soon as physical access or monitoring authority is asserted. The fifth convergence point is the Indian subcontinent, which is not merely a destination but a relay, aggregating cables from the Middle East, Africa, and Southeast Asia, creating dense optical fan-in combined with heavy amplification, and from a physics perspective, amplification plus density inevitably increases leakage opportunities regardless of protocol design. The sixth convergence point is Singapore, which acts as the optical switchboard of Asia, routing traffic between East Asia, South Asia, Australia, and Europe through a remarkably compact geographic footprint where efficiency and economic centrality are paired with structural fragility, because interception here does not require many taps, only the correct ones placed at aggregation points. The seventh convergence point spans East Asia, particularly Japan, South Korea, and Taiwan, where Pacific cables terminate alongside intra-Asia routes and US-Asia backbone links, producing high-quality, high-repetition optical signals that are ideal for interception, demonstrating that technological sophistication does not equate to security when the governing constraints are optical physics rather than protocol elegance. The eighth and often overlooked convergence point is Central America and the Caribbean Basin, which connects North America, South America, and transatlantic routes through shallow waters, nearshore paths, and fragmented jurisdictions, creating physical accessibility and legal ambiguity that make interception feasible without deep ocean operations. What all 8 of these convergence points have in common is that they compress global traffic into manageable physical locations, and that compression breaks the assumptions behind classical encryption models, quantum security proofs, and end-to-end narratives alike, because once communication becomes physical, security becomes a hardware and optics problem first, a cryptographic problem second, and a theoretical problem last, which is why understanding where interception happens is the prerequisite to understanding how it happens inside the cable itself. What you're looking at here is not a wire in the casual sense, it's a layered, engineered system designed to survive pressure, corrosion, and decades of continuous operation on the ocean floor. And every one of those layers exists for a reason that has nothing to do with security. The outer sheath and the steel armoring are there to protect against anchors, fishing gear, and abrasion, not interception, while the copper conductors running alongside the fibers exist solely to deliver power to optical repeaters spaced tens of kilometers apart. At the center of all of this sits the optical core, bundles of single-mode fibers carrying enormous volumes of traffic as pulses of light, multiplexed, amplified, and shared across wavelengths that were optimized for efficiency, not secrecy. What matters here is that power and data are co-located, that multiple fibers travel together inside the same physical structure, and that none of this was designed with the assumption that the cable itself might be treated as an adversarial environment. Once information enters this system, it is no longer abstract or logical. It is physical, continuous, and governed by material properties like refractive index, bending tolerance, and signal loss, which means that understanding how these layers are built is the prerequisite for understanding how information can be observed, influenced, or extracted without ever cutting the cable or interrupting service. What we see here is a fundamental mismatch between what subsea cables are designed to survive and what security actually requires them to resist. The steel armoring, outer sheaths, and protective layers you see here exist to defend against mechanical and environmental threats, anchors dragging across the seabed, fishing gear entanglement, abrasion against rock, pressure at depth, corrosion over decades, and slow movement of the ocean floor itself. All of that engineering effort is aimed at keeping the cable operational, not private. From a security standpoint, these layers solve availability problems, not confidentiality problems, because none of them are designed to prevent observation of the optical signals traveling inside. Light continues to propagate through the fiber regardless of how thick the steel around it is. Evanescent fields still form at the glass boundary. Refractive properties still respond to proximity and bending, and electromagnetic and optical coupling remain possible wherever power and data coexist inside the same physical structure. The critical point is that the original threat model assumed damage, not surveillance, which means the cable is treated as something that might be broken but not something that might be quietly watched. As a result, armoring creates an illusion of security by emphasizing durability while leaving the underlying information channel governed entirely by physics, where gentle, non-invasive interaction can extract signal without cutting the cable, interrupting service or triggering alarms, and where the strongest protective layers stop exactly at the steel. Here we see the physical reality of how information actually moves through long-haul fiber, because despite how it's often described, light inside an optical fiber is not sealed, boxed, or isolated in the way security abstractions imply. In single-mode fiber, information propagates as an electromagnetic field guided by a refractive index boundary between the core and the cladding, where the core has a slightly higher refractive index than the surrounding glass. That difference is what enables total internal reflection, allowing light to remain guided over thousands of kilometers, but it is also what fundamentally prevents the signal from ever being perfectly confined. Even under ideal conditions, a portion of the optical field extends beyond the core into the cladding as an evanescent field, decaying exponentially but never reaching zero, which means the signal is not just traveling through the center of the fiber, it is physically interacting with its surroundings along the entire path. This is not a flaw in manufacturing or deployment, it is an unavoidable consequence of Maxwell's equations applied to dielectric waveguides. The moment data is encoded onto light and launched into fiber, it becomes a continuous physical field governed by geometry, material properties, and boundary conditions, not a discrete object protected by protocol logic. That distinction matters because any interaction that alters those boundary conditions, even slightly, can influence how light propagates, how much power remains confined, and how much information leaks outward. This is the foundation on which everything that follows is built, because once you understand that optical signals are guided rather than contained, you can begin to understand why observation, measurement, and extraction do not require breaking the fiber, interrupting service, or violating any obvious operational limits. Only an understanding of the physics the system has been relying on the entire time. This graph shows why loss is not an anomaly in fiber systems, but a planned, budgeted quantity, and why that planning is exactly what creates room for interception. Optical signals do not propagate indefinitely. They decay with distance due to absorption, scattering, bending losses, splices, and connectors, all of which are accounted for in what engineers call a link budget. On the right, you see that budget broken down explicitly, starting with transmit power at the source, then subtracting known connector and splice losses, continuous fiber attenuation over distance, and finally reserving a margin above receiver sensitivity to ensure reliable operation under non-ideal conditions. On the left, that same reality is visualized as an attenuation curve, showing optical power decreasing predictably as a function of distance, not as a failure mode, but as expected behavior. The critical point is that systems are designed to tolerate loss up to a known threshold, which means there is an allowable window where signal degradation does not trigger alarms, does not interrupt service, and does not violate operational specifications. That window, often referred to as margin, is not empty space. It is where quiet interactions with the fiber can occur. Any process that extracts a small amount of optical power, perturbs propagation slightly, or increases attenuation without exceeding expected limits can hide inside this budget and remain indistinguishable from normal aging, environmental variation, or manufacturing tolerances. This is why loss budgeting is not just an engineering convenience, but a security boundary, because once you understand how much loss the system expects and accepts, you also understand how much interaction it can absorb without noticing, which is exactly the numerical foundation that interception techniques exploit. Long-haul fiber systems do not work by simply launching light at one end and hoping it survives the journey. As optical signals propagate, power decays continuously due to attenuation, dispersion, and scattering, which means that over large distances the signal would eventually fall below usable levels. To make global fiber possible, the system inserts repeaters and optical amplifiers at regular intervals, devices that actively intervene in the signal path by boosting, reshaping, or regenerating the optical signal before sending it onward. These are not passive components. Each amplifier represents a point where the signal is measured, amplified, and re-emitted, restoring power that was intentionally allowed to decay between nodes. From an engineering standpoint, this is what enables transoceanic communication. From a security standpoint, it introduces a critical assumption that these intermediate points are trusted. The moment a system relies on repeaters, the channel is no longer end-to-end in a physical sense, because information does not simply pass through unchanged. It is actively handled at each node. Power drops between repeaters, rises sharply at each amplification stage, and then decays again, creating a repeating pattern of loss and recovery that defines where signals are weakest, where margins are largest, and where interaction is easiest to conceal. This architecture works brilliantly for reliability, but it also means that security is no longer determined solely by what happens at the transmitter and receiver, but by every location in between where the signal is strong enough to be amplified, processed, and sent forward as if nothing happened at all. In modern fiber systems, a single strand of glass does not carry a single stream of information. It carries many independent data channels simultaneously, each encoded onto a different wavelength of light and combined through multiplexing before entering the fiber. These channels coexist in the same physical medium, overlapping in space, time, and electromagnetic field, even though they remain logically separated at the protocol level. From an engineering perspective, this is what makes fibers so powerful. Enormous capacity is achieved by stacking wavelengths on top of one another and allowing them to propagate together over long distances. From a security perspective, it means that every physical interaction with the fiber occurs in the presence of multiple data streams at once. Any perturbation of the optical field, any leakage, coupling, or observation does not interact with a single channel in isolation, but with a superposition of signals whose separation only exists after demultiplexing at the receiver. The important consequence is that the fiber does not carry discrete, independent pipes of data. It carries a shared physical field that is later mathematically disentangled. Once you understand that, it becomes clear why interception, measurement, and information gain are governed by physics first, and protocol definition second, and why analyzing what can be observed requires moving beyond diagrams and into quantitative models of power, noise, and signal separation, which is exactly where we go next. Let's walk through this carefully, step by step, and make sure every number on this screen is clear and justified. On the left side, we start by defining a representative real-world long-haul fiber span, not a hypothetical system. We assume a wavelength of 1550 nanometers, which is the standard C-band used in almost all long-distance and sub-sea fiber deployments. We assume standard single-mode silica fiber, the kind that is actually buried under oceans today. That fiber has a typical attenuation of about 0.2 decibels per kilometer, meaning that for every kilometer the signal travels, it loses 0.2 decibels of power. We then assume an amplifier spacing of 80 kilometers, which is a common order of magnitude distance between optical amplifiers in long-haul systems. If you multiply the attenuation, 0.2 decibels per kilometer, by 80 kilometers, you get 16 decibels of fiber loss across that span. On top of that, engineers budget an additional 1 decibel for connectors, splices, and other imperfections, bringing the total expected loss for the span to 17 decibels. We then assume a transmit power of 0 decibel milliwatts, which is 1 milliwatt of optical power, and a receiver sensitivity of -20 decibel milliwatts, which is the minimum power the receiver needs to reliably detect the signal. Subtracting the total span loss from the transmit power gives an expected received power of -17 decibel milliwatts. Comparing that received power to the receiver sensitivity gives a margin of 3 decibels, meaning the system is operating 3 decibels above the minimum required level. That margin is intentional. Engineers design it in so the system can tolerate aging, temperature changes, repairs, and manufacturing variation. Now we move to the right side of the slide, where we interpret what that margin actually means. If operators assume they want at least 1 decibel of margin remaining before they consider something abnormal or alarming, then out of the 3 decibels of total margin, roughly 2 decibels are effectively invisible. That 2 decibel window represents additional loss that can be introduced without triggering alarms or service disruption. To translate that into intuition, adding 0.1 decibels of loss corresponds to extracting about 2.3% of the optical power. 0.2 decibels corresponds to about 4.5%. Half a decibel corresponds to roughly 11%, and 1 full decibel corresponds to about 20% of the power. The key takeaway is that very small changes in decibels correspond to non-trivial fractions of signal power, and those changes can exist entirely inside normal operating tolerances. Nothing on this slide requires breaking the fiber, interrupting traffic, or violating specifications. Every value shown here lives inside what the system already expects to see during normal operation. This table shows how amplifier spacing directly controls how much optical loss can be hidden without triggering alarms, and it does that by changing the amount of margin engineers are forced to leave in the system. We're keeping all assumptions the same as before. Same fiber, same wavelength, same attenuation, and changing only one variable: the distance between amplifiers. At 40 kilometers, fiber loss is about 8 decibels, and after adding a 1 decibel allowance for splices and imperfections, the total span loss is 9 decibels. Starting from 0 decibel milliwatts transmit power, that leaves a received power of -9 decibel milliwatts. Compared to a receiver sensitivity of -20 decibel milliwatts, the system has 11 decibels of margin, which means that even after reserving 1 decibel as a safety floor, roughly 10 decibels of additional loss could be introduced without raising alarms. At 60 kilometers, the same calculation leaves 7 decibels of margin and about 6 decibels of hidden loss. At 80 kilometers, which is a very typical long-haul span, the margin drops to 3 decibels, leaving about 2 decibels of loss that can be concealed. Finally, at 100 kilometers, the system is already operating below the receiver sensitivity, meaning there is effectively no room left to hide anything without risking failure. The key point is that security does not improve monotonically with distance. Shorter spans have enormous hidden loss windows, longer spans have almost none, and typical engineering choices fall squarely in the middle, where a small but very real amount of covert interaction can be hidden inside what the system already considers normal operation. As optical power leaves an amplifier, it starts at its maximum value and then decays smoothly as it travels down the fiber due to normal attenuation. That decay is predictable, engineered, and expected, which means the highest signal power, and therefore the largest margin, exists immediately after the amplifier output. This is why an attacker does not choose a random point along the span. The optimal location is right here in the high power region near the amplifier, where a small extraction of optical energy represents a tiny fraction of the total signal and can be hidden well inside normal operating tolerances. As distance increases, power drops, margins shrink, and the ability to siphon signal without detection rapidly disappears. The shaded region on the right shows the hidden loss window, which only exists as long as the remaining margin stays above the alarm threshold, typically on the order of 1 decibel. The practical implication is simple but uncomfortable. Interception is easiest where systems are working best. The very places engineered for reliability, high signal strength, and clean amplification are the same places where discrete interaction with the fiber is hardest to notice and easiest to conceal. In practice, optical power is not extracted by cutting a fiber or inserting an obvious splitter, but by exploiting how light behaves when the physical geometry of the fiber is gently altered. Under normal conditions, light remains guided inside the core through total internal reflection, with a small evanescent field extending into the cladding. When the fiber is bent beyond a critical radius, that evanescent field grows stronger and extends farther outside the glass, allowing a nearby coupler to interact with it. This interaction does not interrupt transmission. Instead, it siphons off a small fraction of optical power while the majority of the signal continues downstream. The key point is that this leakage is continuous and analog, not binary. By carefully controlling the bend radius and coupling strength, an attacker can extract power gradually, introducing only a small additional loss that blends into the system's existing attenuation budget. From the perspective of the network, nothing unusual has happened. The signal is still present, still synchronized, and still within expected operating margins. From a physical standpoint, however, information has already left the fiber. This is why bend-induced leakage and evanescent field coupling are so effective. They work with the physics of guided light rather than against it, allowing observation and extraction without triggering alarms, service disruption, or obvious signs of tampering. In the real world, optical interception hardware does not look like a splitter spliced into a cable, and it does not require cutting or interrupting service. What you're looking at here is a clamp-on, in-service fiber tap. Hardware designed specifically to exploit the physics of guided light rather than violate the integrity of the fiber. The device mounts around an intact cable and applies controlled mechanical pressure at a precise location, bringing an optical coupler into close proximity with the cladding. At that point, it is not accessing the core directly. Instead, it is interacting with the evanescent field that naturally extends beyond the core cladding boundary during propagation. Because the fiber remains continuous and undamaged, the majority of optical power continues downstream exactly as expected, while a small fraction is coupled out into a secondary fiber. From the network's perspective, nothing has been disconnected, rerouted, or broken. There is no sudden outage, no obvious reflection spike, and no event that looks categorically different from normal attenuation. The amount of power extracted is controlled mechanically and optically, allowing the tap to stay well within the hidden loss window we quantified earlier. This is why these devices are so effective. They are passive, analog, and incremental. They do not announce themselves as an attack. They behave like a slightly worse piece of fiber. And because the cable remains in service the entire time, traffic continues to flow, timing remains intact, and higher-layer protocols see nothing more than expected link behavior. The critical takeaway is that this kind of interception is not hypothetical or exotic. It is enabled by commercially realizable hardware operating entirely within the physical assumptions of long-haul fiber systems. Once this capability exists, the question is no longer whether interception is possible, but how much information can be extracted before anyone notices, and under what conditions detection becomes fundamentally unreliable. When operators look for physical tampering on long-haul fiber, this is essentially what they see. An OTDR sends short optical pulses down the fiber and measures backscattered light to reconstruct signal strength as a function of distance. Large reflections, sharp discontinuities, or sudden step changes stand out clearly and are easy to flag. Those are the events detection systems are designed to catch. What they are not designed to catch are small, smooth changes that fall inside the natural variability of the link. As the signal propagates, its power decays steadily, and the backscatter trace becomes increasingly noisy due to scattering, temperature effects, polarization changes, and instrument resolution limits. That noise floor grows with distance and averaging, which means very small additional losses simply disappear into it. The highlighted region here represents tap-induced loss that is real, measurable and physically present, but indistinguishable from normal fiber behavior. From the detector's perspective, there is no clear signature that says, "This is an attack," rather than "This is slightly worse fiber." Tightening detection thresholds does not solve this problem, because doing so would generate constant false alarms from benign effects like aging, repairs, or environmental drift. The uncomfortable implication is that detection systems are optimized for reliability, not adversarial certainty. If an interception introduces loss gradually and stays below the system's alarm thresholds, the monitoring infrastructure does exactly what it was designed to do. It ignores it. This is not a failure of instrumentation. It is a consequence of how fiber behaves and how detection systems must operate to keep global networks stable. Detection thresholds are not set arbitrarily. They are the result of a trade-off that every large-scale network operator is forced to make. As detection sensitivity increases, the system becomes more capable of flagging very small deviations from expected behavior. But that increased sensitivity does not just amplify real attacks. It amplifies everything: temperature drift, polarization changes, fiber aging, microbends, repairs, and measurement noise. The curve here captures that reality. On the left side, with low sensitivity, the system is stable but blind to subtle events, which means small, carefully engineered attacks go unnoticed. As sensitivity is increased, detection improves marginally at first, but false positives rise much faster than true positives. Beyond a certain point, the system becomes operationally unusable, generating frequent alarms for benign conditions and forcing operators to either ignore alerts or disable detection entirely. This is why thresholds are deliberately set below what security theory would prefer. Networks are optimized to stay online, not to enforce adversarial certainty. The uncomfortable consequence is that there exists a region where interception activity can occur, remain physically real, and still be classified as normal behavior by the detection infrastructure. That region is not an accident or a bug. It is the inevitable outcome of balancing reliability against sensitivity in a noisy physical system. Interception is not a single action. It is a process, and that process begins with access rather than computation. The first step is identifying a viable physical access point, typically a landing station, conduit vault, repeater housing, or other location where fiber can be reached without drawing attention. Once access is established, a clamp-on tap is installed directly onto the intact cable. This hardware does not cut, splice, or interrupt the fiber. It applies controlled mechanical pressure to the cladding, positioning an optical coupler where the evanescent field is strongest and signal power is highest. From there, the extracted optical signal is routed into a signal capture module that conditions, stabilizes, and converts the light into a form suitable for recording. At this stage, the data is still raw optical information, weak, partial, and noisy, but it is continuous and synchronized with the live traffic on the line. Finally, the captured signal is sent off fiber to a recording or processing unit, where it can be stored, filtered, demultiplexed, and reconstructed over time. None of these steps require service interruption, visible damage, or immediate detection. Each step operates within the physical tolerances of the system, leveraging the same engineering assumptions that keep long-haul networks reliable. The important takeaway is that interception succeeds not because systems are poorly built, but because they are built to prioritize availability, stability, and scale. Properties that adversaries can systematically exploit when given sufficient access and time. Intercepted optical signals are not immediately usable in the form they are captured. What leaves the tap is a weak, noisy optical waveform containing a mixture of channels, noise, and distortions introduced by the fiber, the tap itself, and the environment. The first step in reconstruction is filtering, Narrowband, optical, and digital filters suppress out-of-band noise and isolate the frequency ranges of interest, improving signal-to-noise ratio without requiring large amounts of raw power. Once filtered, the signal is amplified. This amplification is not about restoring original launch power, it is about lifting the signal above processing thresholds so that timing, phase, and amplitude information can be extracted reliably over time. At this stage, the signal is still composite. Multiple data streams are superimposed just as they were in the fiber. The next step is demultiplexing, where individual wavelength channels are separated using optical filters or digital signal processing techniques. Each recovered channel is then integrated over time, allowing weak but consistent patterns to emerge from noise. With sufficient observation time, error correction, clock recovery, and protocol-level redundancy do much of the remaining work. What matters here is that interception does not require perfect copies of the original signal. It requires consistency. Even partial, low-power captures become valuable when combined with modern signal processing, long integration windows, and knowledge of the protocols being used. This is why physical interception scales with patience rather than precision. Once raw, optical data is captured, the problem transitions from physics to computation, where time, storage, and processing power steadily convert weak observations into structured information. Even when an adversary cannot perfectly reconstruct the encrypted payload, interception still produces valuable information. What survives first are traffic patterns and correlations. Who is communicating with whom, how often, and in what sequences? Above that sits metadata, timing, flow direction, session duration, and packet ordering, which remains intact even when payloads are unreadable. Packet timing and sizes leak next, revealing behavioral fingerprints that can identify applications, protocols, and even user activity through correlation alone. Only at the lowest layer does encryption reliably protect the payload content itself, and even then only against direct inspection. The important distinction is that encryption operates on data, not on the physical act of communication. As long as information must move through time and space, it creates structure. That structure persists under noise, partial capture, and imperfect reconstruction. With sufficient observation time, aggregation, and correlation, these higher layers often provide strategic insight that rivals or exceeds the value of raw content. This is why interception remains effective even when cryptography is mathematically sound. Most of what matters operationally is not hidden inside the payload, but revealed by how communication happens. Most security models begin by assuming a clean, sealed channel between a sender and a receiver. In that model, encryption, or even quantum key distribution, protects the information flowing across the link, and the physical medium is treated as an abstract conduit that either works or fails. On the left, that assumption looks reasonable. A locked channel, mathematically secure with no room for observation. But the right side reflects how communication actually happens. Real channels exist in the physical world. They run through conduits, landing stations, repeaters, and shared infrastructure. They leak timing information, metadata, and side channel signals simply by existing in space and time. Even when payloads are perfectly encrypted, the act of communication still produces structure. When data moves, how often it moves, how large the bursts are, and how flows correlate across the network. None of that is addressed by cryptographic proofs, because none of it violates the encryption model. This is the core disconnect. Security models protect data, not physics. When those models are deployed onto real infrastructure, they inherit the assumptions of the hardware, the environment, and the detection thresholds we've already discussed. That gap between the model and the deployment is where interception lives, and it exists regardless of how strong the cryptography is on paper. Quantum security is often presented as fundamentally different from classical encryption, offering provable guarantees rooted in physics rather than computation. In the idealized model, single photons travel directly from a quantum sender to a quantum receiver, and any attempt to observe them introduces detectable disturbance. In that world, the channel is clean, loss is minimal, and no intermediate devices exist between the endpoints. But real deployments do not resemble that model. Real fiber introduces loss, which forces the introduction of amplifiers, repeaters, or trusted nodes to extend range. Each of those elements breaks the original end-to-end assumption by handling the signal locally, reintroducing classical trust into what was supposed to be a purely quantum channel. At the same time, the physical layer leaks timing information, metadata, and side-channel signals that are entirely outside the scope of quantum security proofs. None of this violates the mathematics of QKD. The proofs still hold, inside their assumptions. The failure occurs when those assumptions collide with geography, infrastructure, and operational necessity. Undersea cables, long-haul fiber, and global networks require compromises that move systems away from the idealized quantum model and back into the same physical reality we've been examining throughout this video. The result is not that quantum security is useless, but that it does not eliminate the attack surface created by real-world deployment, and it cannot close the gap between what is provably secure on paper and what is observable in practice. Defensive measures around long-haul fiber do work, but only within well-defined limits. Monitoring systems can detect large disturbances, sudden loss events, or obvious physical damage, but they are not designed to reliably flag small, passive taps that remain inside normal operating tolerances. Redundancy improves availability and resilience, ensuring traffic continues to flow even when links fail, but it does nothing to prevent signal leakage along individual paths. Anomaly detection can identify dramatic changes or correlated failures, yet it struggles with slow, incremental deviations that resemble natural variation. Audits and inspections help uncover compromised infrastructure over time, but they are periodic by nature and cannot continuously guarantee the absence of passive interception. Together, these layers reduce risk and raise the cost of attack, but none of them eliminate the physical exposure inherent in optical communication. The uncomfortable reality is that once data must traverse shared, long-haul physical infrastructure, perfect secrecy becomes an aspiration rather than a property. Defense in this domain is about mitigation, not elimination, and security posture is defined by how much risk remains acceptable in exchange for keeping global networks operational. When data moves across the world, it does so through physical systems governed by physics, not by cryptographic intent. Undersea fiber links leak information not because they are poorly engineered, but because they are engineered to be reliable at global scale. Interception in this environment is passive, incremental, and designed to remain indistinguishable from normal operation. Detection systems reflect that reality. They prioritize stability and uptime, not perfect adversarial detection. Even when payloads are encrypted or protected by quantum protocols, contextual information such as timing, metadata, and traffic patterns continues to leak. And while quantum security offers powerful guarantees under ideal assumptions, those guarantees weaken when deployed over real infrastructure that requires loss tolerance, amplification, and trust. In the end, defenses can reduce risk and raise the cost of attack, but they cannot eliminate the physical exposure inherent in long-haul communication. Understanding that gap between theory and deployment is the first step toward realistic security. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, You can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.